Hello, and welcome to our Precalculus course. My name is Bruce Edwards, and I'll be your guide for the next 36 lectures as we cover topics such as algebra, logarithms, trigonometry, linear equations, and many, many other topics. Before we get started, let me take a moment to tell you a bit about myself. Who is Bruce Edwards? Well, I'm a professor of mathematics at the University of Florida. That's down in Gainesville, Florida. And I've been there since 1976. I graduated from Stanford University a long time ago, in 1968, with a degree in mathematics. And then I joined the Peace Corps. And I worked in Colombia, South America, for 4 years. I taught mathematics at a university there in Spanish. I returned to the United States in 1972 and went to graduate school and received my doctorate in mathematics from Dartmouth in 1976, and I've been at Florida ever since. I'm a research mathematician. The broad area of my research is called numerical analysis. It's kind of computer solutions to applied engineering and science problems. And in particular, I'm very interested in studying how calculators work. What goes on inside a calculator when you push a button? Now, we'll be using calculators in this course every so often, and so I highly encourage you to get a hold of a graphing calculator. They're a lot of fun to use and will aid us in verifying solutions and seeing pictures of mathematical ideas. I'm also a textbook author. I've written many, many books with my co-author Ron Larson at Penn State University. And in fact, the content of this course, these 36 pre-calculus lectures, the content's pretty much based on one of our textbooks. That said, if you have almost any textbook with the title Precalculus or Algebra and Trigonometry, that'll serve you well to sort of supplement what we do in these lectures. So, what is precalculus? What are we going to be studying? At one level, it's exactly what the name says. It's preparation for calculus. It's the content of all the mathematics you need to be successful in a calculus course. Its main topics are algebra and trigonometry, but then there's some other topics that we'll talk about in a minute. But it's not only just the preparation for calculus. It's a course that has applications in all disciplines. And in fact, at my university, precalculus is a prerequisite for many, many majors. Thousands of students take precalculus at the University of Florida every year. And another reason that it's a really great course, I think, is it has some neat problems and some beautiful applications. Let me talk about some of those applications that we'll see in upcoming lectures. We'll talk about radioactivity and carbon dating. In finance, compound interest. We'll see parabolic mirrors, reflecting mirrors, and we'll talk about something called whispering galleries. When we get into trigonometry, which is a big bulk, a big chunk of this course, we'll talk about how you would calculate the height of a tree, and we'll learn about harmonic motion. Early on in the course, when we study complex numbers, we'll see the beautiful fractals and the famous Mandelbrot set. Other applications, we'll talk about how SAT scores are distributed. We'll take a peek at the Leaning Tower of Pisa. Near the end of the course, in fact, at the very end of the course, I'll spend some time talking about GPS devices, those magic little things that tell you where you are on the Earth. But overall, precalculus has applications in all of science, chemistry, physics, engineering, etc. But most important, perhaps, it has applications to calculus. And as we proceed in this course, I will stick in little tidbits that are really calculus comments based on the precalculus we're looking at that moment. Great. Let's get started. Let's dig in. Let's do some math. I'd like to begin with the concept of function. This is a key concept in pre-calculus and in fact in all of mathematics. So I think it's important to get a firm understanding of what a function is, see some examples, and pick up some of the terminology. In this course, we'll look at all kinds of functions: linear functions, polynomial functions, exponential, logarithmic functions, and of course the trigonometric functions. Let's do an example. What is a function? Well, I can explain it best with a simple example, I think. Let's consider, say, the following very simple function, x squared. And by that I mean the following. You give me a value of x, and I'll square it, and that will be the output of the function. So the input is a value x, and the output is the square of that number. And we write that as f of x equals x squared. For every value of x, out comes its square. For instance, f of 2, that means evaluate the function at 2. 2 squared is 4, so f of 2 is 4. What about minus 2? Well, f of minus 2 is minus 2 squared. Minus times minus is plus, so it's 4 again. How about f of 0? 0 squared is 0, so f of 0 is 0. Then there's some concepts that go along with functions. What's the domain of this function? Domain means what values are you allowed to plug into this function? Well, we can take any real number and evaluate its square. And then there's a concept called range. And range is the set of all the outputs. And notice the range in this function, you don't get back any negative numbers, do you? So the range here are all values of the variable greater than or equal to 0. All numbers greater than or equal to 0 because you can't get a negative value out. Let's formalize some of these ideas. What's the precise definition of function? Well, a function f from a set A to a set B is a relation that assigns to each element x in the set A exactly one element y in the set B. So x here goes to the y value over here and to a unique y value. The set A is called the domain. Those are the inputs. And the range is the set of all the outputs. And of course, that's a subset of B. And our notation will usually be y equals f of x being an input, y being the output. Let's look at another example. Suppose I say, can you graph the function f of x equals 2x plus 3? What's the picture look like for this function? Well, let's plug in some values. Let's take the function f of x equals 2x plus 3, and to get a handle, I like to do this a lot with functions, I like to plug in some numbers and see what's going on. So let's plug in some numbers. Suppose I plug in 2. What's f of 2? Well, you would plug in 2 for x and get 2 times 2 is 4 plus 3, or 7. How about f of 0? Easy, 2 times 0 is 0, plus 3 is 3. How about minus 2? That'll give minus 1. So by plugging in certain values, I can then plot those numbers in the xy coordinate system and connect them with a curve. And in fact, in this case, it'll be a straight line, won't it? But before we look at the picture, ask yourself the following. What's the domain of this function? What are we allowed to plug in for x? And I hope you see any real numbers okay here. What about the range? What comes out? And again, although that's a more difficult question in general, all values come out. The range, again, is all real numbers. And this is an example of a polynomial function. It's a linear polynomial function in the sense that the x power here it's x to the first power. Here's a graph of that linear function 2x plus 3. Notice it passes through those 3 points we evaluated, and we've joined them with a straight line. And this is a straight line of slope 2 and y-intercept 3. Let's do another example, slightly more difficult, but again, a very important example in pre-calculus and in calculus. The square root function. F of x equals the square root of x. Let's stop for a moment and think about the domain. What values am I allowed to plug into the square root function? Well, yeah, you can't plug in negative numbers, can you? We can't take the square root of minus 1. in the real numbers. So the domain here is all x greater than or equal to 0. And in fact, the range again here is the same. It'll be all real numbers greater than or equal to 0. Here's a graph of the square root function. I obtained this by some point plotting, calculating some square roots of numbers and plotting them in the plane. You could also obtain this graph with your graphing calculator. I invite you to do that and see if it looks sort of like this picture here. Some more terminology. In the notation y equals f of x, x is often called the independent variable and y the dependent variable. And the reason is x can kind of be anything it wants in the domain, so it's kind of independent. But once you've selected your x, y depends on it. Okay, so that's kind of a nice terminology. And y is often called the value of the function at x. And the issues that will come into play as we proceed studying functions will be issues of domain and, of course, graphs and range. But domain will be a crucial issue. What are some of the things that can go wrong when you think about the domain of a function? Well, we just saw one of the problems, square roots. Square roots of negative numbers, and in fact, fourth roots, sixth roots, etc. So when you see a root symbol, be a little nervous. Another issue that comes up is dividing by 0. You can't divide by 0 in math, so that will sometimes limit the domain as well. And furthermore, in some applied problems, the domain is restricted because of the application. If you're dealing with, say, a problem with area, well, you'd want to make sure that your domain is greater than or equal to 0. In fact, greater than 0, because areas are positive. And by the way, as I said earlier, although the domain is something we'll talk about and define and look at in all these functions, range is much more difficult to determine in general, and we won't get too involved with that. Let's do another example. The absolute value function. One of my favorite functions in calculus, and I'll tell you why in a moment. But here's how it's defined. The absolute value of a number, and it's denoted with two vertical lines around x. It's x in the case where x is greater than or equal to 0, but it's minus x if x is negative. That might seem kind of weird, so let's evaluate it at certain numbers. What's f of 3? Well, 3 is positive, so f of 3 is 3. What's f of 0? That's greater than or equal to 0, so f of 0 is 0. Now comes the tricky part. What's f of minus 5? Well, the definition says because minus 5 is less than 0, the output will be minus 5, minus x, minus 5, which makes it positive. In other words, the absolute value of a number is always non-negative, isn't it? Okay, so its domain is all x. You can take the absolute value of any real number, but the range is the set of all non-negative real numbers. And if you look at the picture of this, you see it's kind of a V-shaped curve. It's not, I won't even say curve. It's two lines coming together at the origin in a sharp corner. And that's why this function's interesting in calculus. It's continuous in the sense that you can draw it without lifting up your pencil. But it has a sharp corner down there at the origin, and that has an important, that's an important feature in calculus courses when you have sharp corners. Let's look at another function that's a little more complicated. This function, again, is defined by two rules, and here's how it goes. The function f of x equals x squared if x is less than 1, and it equals the square root of x minus 1 if x is greater than or equal to 1. So again, let's become comfortable with this function by plugging in some numbers and seeing the output. What's f of minus 1? Well, minus 1 is the top rule. So f of minus 1 would be minus 1 squared, or 1. How about f of 0? That again is the top rule. F of 0 would be 0 squared, or 0. How about f of 1? 1's kind of the boundary between these two rules, isn't it? But it tells us to use the bottom rule because 1 is greater than or equal to 1. So it's the square root of 1 minus 1, or 0. And how about f of 5? Well, f of 5 would be the square root of 5 minus 1, so that's the square root of 4, or 2. So, how would you graph this function? You would take these points and maybe a few more, plot them in the XY coordinate system, and try to figure out what it looks like. But you can kind of see what's going to happen. For x less than 1, this looks like a parabola x squared, cut off, of course, at 1. And then the other part of the curve will look like the square root function, but it's been shifted to the right 1 unit. Interesting looking, isn't it? It's got two pieces. And you see that part of it's kind of a parabola, and the other part looks like our friend, the square root function. And this kind of function, again, is important in calculus because you can't draw it without lifting up your pencil. It's not continuous when x is 1. All right. You be the teacher now. I'll try to do this kind of you be the teacher episode in many of my lectures as we go along. I think it's kind of fun to sort of plant yourself in the shoes of a teacher and see how you would answer certain questions. Suppose a student comes up to you and shows you the following graph and asks, "Teacher, can that be the graph of a function? And if it is, what's the formula for that function?" Well, how would you answer that, student? Could that be the graph of a function? Right. It can't be. That cannot be the graph of a function. And here's why. For a given x value, you're supposed to have a unique y value. But if you were to pick an x value, you could go up to the top and get a y value, or go down and get a different y value. So that's not the graph of a function. And in fact, we're illustrating here what we call the vertical line test. If a vertical line hits a graph in more than one point, as it did in that previous picture, then the graph is not the graph of a function. Okay, so that's a nice test, a visual test for functions. All right. Let me make a couple other comments about notation and things. In this business of mathematics, we don't always say y equals f of x. We often will use a different letter. We might use g of x instead of f of x. And even worse, we might use a different letter than x. We might use a Greek letter. We might use w, or in the following example, I'll use the letter t. And I'll use t because the following example deals with time. So let's look at this example. Suppose you have $1,000 and you're investing it at 5% interest, compounded annually. How much will you have, say, after t years? Let's see how much you'll have. Okay, after 1 year, how much will you have? Let's figure it out. You start off with $1,000 and you earn interest on that $1,000 at 5%, which means you multiply by 0.05. Okay, so we have, after 1 year, the original $1,000 plus the interest we earned, which is 1,000 times the interest rate, 0.05, or it's 1,000 times 1 plus 0.05. And here I've factored out the 1,000 and left it as 1 plus 0.05, which can be written as 1.05 or 1,050. So in a nutshell, after 1 year, I've earned $50 interest at 5% on my $1,000 deposit. Okay, what happens the next year? Ask yourself this question. After year 2, will I earn another $50? Well, compound interest doesn't quite work that way. You're going to actually earn a little bit more than $50 the second year. Watch how it goes. After 1 year, we have 1,000 times 1.05. That's how much we earned after 1 year. And that amount sitting in the bank. And it earns interest. That new amount, the amount after 1 year, earns 5% interest. So after 2 years, I have the initial amount, 1,000 times 1.05, plus 5% of that amount. So it's 1,000 times 1.05 times 0.05. Now factor again. It's kind of a complicated factorization. Pull out the 1,000, pull out the 1.05, and you're left with 1 plus 0.05. Kind of neat, isn't it? You're left with 1,000 times 1.05 times 1.05, or 1.05 squared. And if you punch that on your calculator, you'll see that you now have $1,102.50. So that second year, you made a bit more than $50, didn't you? That's the power of compound interest. It's really good stuff. And in fact, if you continue this argument, I think you can see that after 3 years, what would you have? Well, you'd have 1,000 times 1.05 cubed. And after 4 years, it'd be to the fourth power. And in fact, after t years, where t is any positive integer, you would have 1,000 times 1.05 to the power t. So this is a nice example, a nice function concerned with compound interest. Later on in this course, we'll delve into other kinds of compound interest, and we'll see generalizations of this fairly straightforward formula. Now, the concept of function has a long history and complicated history. Historians seem to think that the idea of function dates back to Persian mathematicians back in the 12th century. The word function was first used probably in 1673 by Gottfried Leibniz. He wrote it. He used that term in some papers he wrote. Leibniz is very well known as one of the co-founders with Isaac Newton of calculus. Leibniz and Newton both lived in the 1600s and independently developed many of the ideas that today form our subject matter called calculus. And of course, as I've said over and over, and as you'll notice as we progress through our 36 lectures, the concept of function is fundamental in precalculus as it is in all of mathematics. So let me go back now to a little bit more discussion of our course. What are we going to be doing in these 36 lectures? Well, basically we'll cover all the topics in a high school or college precalculus course. As I said, we teach precalculus at the University of Florida, and the topics in this course here on our DVDs will be very similar to what we teach at the University of Florida. These courses are sometimes called algebra and trigonometry, but it's basically the same course. The portion of algebra and trigonometry will be the core of this course, but we'll also dabble in some really interesting and important topics that are slightly different. We'll talk about how to solve linear equations. You might have 2 equations and 2 unknowns, or even worse cases, 3 equations, 3 unknowns. We'll talk about something called sequences and series. We'll spend a few lectures on a lovely topic called conic sections, where we'll study parabolas, ellipses, and hyperbolas. We'll bring in parametric equations, which will be a sort of a new kind of function, and polar coordinates. And again, near the end, we'll even have a lecture or 2 on probability. It's always fun, a subject that grew out of gambling. Let me add that our course has a workbook associated with it. And I suggest, as I do to all my students when there's a textbook, look at the workbook if you have time before the lecture. You'll get a feel for what I'm going to cover in the lecture. And then you might read it afterwards. Many of the examples in the workbook are the same as what I'm doing here in the lectures. And then the workbook has some exercises. Usually about 10 per lecture. And I highly recommend you try to do them. It builds a lot of self-confidence. You'll see if you're understanding what I'm talking about, if the ideas are clear to you. Here's some good news. The solutions to these exercises are also in the workbook, so you can go and see if you did the problem right. Remember, in math, practice is really important. It's very healthy to do a lot of problems. That's how a lot of learning takes place. Here's some other good news. Well, I'll tell you the bad news when I'm a lecturer at the University of Florida. If I'm teaching to a large group of students, they can't stop me. If I'm talking away on some math topic, it's very difficult for them to say, "Excuse me, professor, I didn't understand the last 10 minutes. Could you go back and repeat that for me?" That doesn't happen. But you have a great advantage. You can stop the DVD anytime you want. You can go back. You can pause it and come back to it the next day. So that's a real advantage, I think, for these teaching company courses, for the great courses that you can look at them at your leisure. And you can also, of course, take notes, and you can verify what I do in my lectures with your graphing calculator. Again, I highly recommend you carry along a graphing calculator as we do problems. Now, students often ask me, in all the courses I teach, but I'll focus on Precalculus, what makes Precalculus difficult? Why is it hard? And on the one hand, it's not clear it's that hard, but it's often difficult for students. And after all my almost 40 years of teaching, I've kind of boiled it down to two reasons. Kind of simplified it, haven't I? On the one hand, I think it takes practice. I think to be successful in math, and in particular Precalculus, you have to practice. It's much like becoming a good basketball player. If you want to be a good basketball player, it's not enough to watch other people play basketball. You have to shoot the basketball. You have to try to hit some free throws. So practice is crucial, and fortunately we have a workbook where you can practice and check your answers. And the second reason that I think what students stumble in Precalculus is background material. They often go into the math course and they're a kind of shaky on some of the prerequisites for that course. They're kind of like, "Oh, I don't really remember that," and suddenly they're lost. I'm going to make a point as we go through these lectures to indicate the places where there's a Precalculus skill, a skill that's pre-Precalculus, something that needs to be brought in to remind you, "Oh, remember this? You probably did this earlier." And so we're all on the same page. Now, there's some good news about this. Professor James Sellers has two courses with the teaching company, Algebra 1 and Algebra 2. And Professor Sellers and I have coordinated our two courses together. And while they have a little bit of overlap, some necessary overlap, these really are distinct courses. So how can you use this Precalculus course? One use, of course, is the obvious use, hence the name, to prepare you to take calculus. You might be taking your own Precalculus course right now, and you might be studying logarithms, and you're saying, "Well, the teacher did it this way. Let's see how Professor Edwards explained logarithms." Or you might have taken Precalculus, trigonometry, algebra a long time ago, and you want to refresh your knowledge. You might be in the workplace, and you want to see how Precalculus can be used in everyday applications. And what I think is often most interesting, you might be a teacher yourself or a tutor, and you'd like to see how other people, me, explain certain ideas. It's kind of fun to watch somebody else try to explain trigonometry. So, what now? What are we going to do next lecture and for subsequent lectures? Well, next lecture I'd like to keep going on functions, and in particular we'll look at polynomial functions. And then after that we'll do some more functions. We'll talk about exponential functions, logarithmic functions, trigonometric functions, and on we go. So I look forward to seeing you next time when we begin our study of polynomial functions. Thank you very much.